Hello friends, this video on structure of atoms part 34 is brought to you by examfear.com. No more fear from exam. Before watching this video, please make sure that you have watched part 1 to part 33. Let's study the filling of orbitals. The filling of orbital depends on the first principle, that is called above principle. We'll discuss this. It also depends on Pauli's exclusion principle and Hund's rule of maximum multiplicity. Also, it depends on relative energies of orbitals. So let's discuss the above principle first. This principle states that in the ground state of atom, the orbitals are filled in order of their increasing energies. Please note, they are filled in order of their increasing energies. If you see the order, if you have for any multi-electron atom, this is the order I told you. Order will depend on n plus L rule. For this, n is 1, L is 0. So this is 1, n plus L. For this, n is 1, L is 0, n plus L is 2. For this, n is 2, L is 1, this is 3. Here, n is 3, L is 0 because S 3. But if you compare these two, the lower value of n is taken first. So this is how we have arranged the orbitals in the increasing order. We have done in the past slide also. We have ordered this in the increasing order, and the electrons are filled first in 1s. If this is filled completely, then in 2s, then in 2p, then in 3p, like that. So a good way to understand this is you can write in this fashion: 1s, 2s, 2p, 3s, 3p, 3d, 4s, 4p, 4d, like that. And then you start like this fashion. You get 2s, then you get 2p, 3s, then you get 3p, 4s, like this. So I'll just show you. It's a good way to learn actually. 2s, 2p. For 3 you get 3s, 3p, 3d. For 4 you get 4s, 4p, 4d, 4f, like that. For 5 you get 5s, 5p, 5d, 5f, like that. Right? For 6 also you get 6s, 6p, 6d, 6f. But nothing more than f is required, so the max I am putting is like that, f only. So you start with 1s, right? You get this 1s, and then you get this 2s. Then you go like this, you get 2p and 3s. Then you get 3p, 4s, right? Again you go back without touching. Again you touch and come 3d, 4p, 5s. Again you go back without touching, and you come back with touching. This is how the order is, and that's exactly the same figure which is here. So this is a easy way to understand, but the logic here is the lower energy, this is lower energy, this is higher energy orbitals. So the lower energy orbitals get filled first, then higher, and it goes on. So this is the first principle which says that the lower energy orbitals get filled first and then the higher energy. Next is the Pauli's exclusion principle. So we have told the lower energy get filled first, but how many electrons can there be in one orbital? That was something not defined. So this guy this principle, Pauli's exclusion principle, says that no two electron in an atom can have same set of 4 quantum numbers. This is the Pauli's exclusion principle. That means for a given L, M, N and MP, N, L, M, MP, this 4 quantum numbers we have, right? Principal quantum number, azimuthal quantum number, this is orientation quantum number, and this is my spin quantum number. So with all 4 this quantum number, I can uniquely identify an electron. That means one electron, no 2 electrons can have same all the 4 values, right? And that clearly means that since this can have only 2 volutes, plus 1 by 2 and minus 1 by 2, that means in one orbital there are 2 electrons, and that we have discussed earlier also, right? So this guy says that no 2 electrons in an atom can have 4 set of quantum numbers. We have 4 set of quantum numbers we discussed. So if we have all the values of N, L, M and MP, we can tell which electron we are talking about, right? And it also states that only 2 electrons exist in the same orbitals. and these electrons must have opposite spin. As I told, this can the magnetic the spin quantum number has only two values. There's a clockwise and anti-clockwise. So it says that in an orbital you can have only two electrons and they should have opposite spin, right? So this means that two electrons can have same value of three quantum numbers, these three, this N, L, M, N, L, but they should have opposite spin. I think we have discussed this earlier also. And the maximum number of electrons in a shell is 2n square. For a given n, for example, 1s I tell, so for 1 I have 2n square, 2s, 2p will have 2 into 2 square, 3s, 3p and 3d. The maximum value in this shell, we shall have all these 3s, 3p, 3d, will have 3 into 3 square electrons. Then we got something called Hund's rule of maximum multiplicity. So till now we have told that, for example, 3p orbital will be filled after 3s, let's suppose, right? But the question is, in 3p shell also, in 3p subshells actually, in 3p subshells, there are three orbitals, 3px, 3py, 3pz, and all have equal energy, correct? Because I'm saying 3p is not the orbital actually, 3p is the subshell. So in 3p subshells we have three orbitals, 3px, 3py, 3pz, and all these 3p have equal energy. Energy is equal in all these three orbitals. So which one will be filled first? We don't know, right? So to avoid this confusion, Hund's rule of maximum multiplicity come to save us. This deals only with in a subcells, if you have orbitals and they have same energy and they are called degenerate orbitals, it deals with filling of electrons in those orbitals. It says that pairing of electrons in orbitals belonging to same subcells P, D or F does not take place until each orbital belonging to that subcell has got one electron. For example, in this case, if you see, there are three 3px, 3py, 3pz. That means we have this is, let's suppose, px, right? So we have or I'll say like this, I'll put one box for px, one for py, one for pz. So it says that first one each will come in all these orbitals. Once it is filled, once it is half filled, then only the second electrons will come. Hope you understand. See, for example, I'll tell you, I have, this is my 3p shell. So this is my 3px, this is 3py and 3pz. One first electron comes, it will come here in this cell. The second electron comes, it should come in the same, this px orbital or py orbital. We don't know. Then this guy comes, Hund's rule of maximum multiplicity. It says that this new electron will come in py, not in px. Why? Because it says that if you see that pairing of electrons does not take place until the each orbitals in that subshell has got one electron. The pairing won't start until each of these orbitals px, py, pz has got one electron. So the next electron comes, will it go to px, py or pz? It should go to pz. Why? Because the pairing will not start until each of the orbitals has got one electron. Now the second electron, the fourth electron now will come to this place, then to this place and then to this place. So this rule was given by, right? So it says that since there are 3 p's, 5 d's and 7 f orbitals, therefore pairing of the electron in these orbitals will start with the entry of, since there are 3 p's, so till third p there is no pairing. From the fourth the pairing will start in p. For d, if you see, if you talk about d, so if you talk about d, for example, I'm talking about d subcells. So d will have 5, 1, 2, 3, 4, 5, right? So we have 5 orbitals for d, dxy, dyz, dxy minus y square, like that. So the first guy, second guy, third electron, fourth electron, fifth electron will be filled like this without pairing. Only the sixth electron will be paired. So if you say the pairing starts from sixth electron. And similarly for f orbitals, if you see, for f we have for F subshells actually 1, 2, 3, 4, 5, 6. Yeah, for F subshell we have 7 orbitals, right? 1, 2, 3, 4, 5, 6, 7 orbitals. So the first electron will come like this, second will be the second orbital, third will be third orbital, fourth, fifth, sixth, seventh. Only from the 8th electron the pairing will start for F orbital. Hope you understand what this guy is trying to say. This guy is trying to say that in a subshell, if you have more orbitals, for example for P we have 3 orbitals, the pairing will start only from the 4th. First, second, third will be without pairing. Only from the 4th the pairing will start. In case of P orbitals, P subshells, there are 5 orbitals, so the pairing will start only from the 6th electron till 5th electron. Each of this electron will be a different orbital and they will be alone. Only for the 6th electron it comes, the pairing starts. It is as good as in the bus. If you see, right, there are, let's suppose 1, 2, 3, 4, 5 empty seats, and if passengers come, they generally want to even if there is a double seat in the bus, right? You must have seen in the bus there are double seats, right, like that. So 1, 2, 3, 4, 5, like this. So if a passenger comes, he'll sit here. The second guy comes, if they don't know each other, so instead of sitting here, he'll prefer sitting here because this guy is an empty seat. Again, one more new guy comes, he will prefer sitting here instead of sitting beside these two guys because he'll get more space. Again, a new guy comes, he'll try to sit in the new space. But then if all these seats are filled, all these double seats are filled with one electron, one person, the next guy comes, he don't have any other choice than to share the seat. Nobody likes to share the seat. Similarly, the electrons don't want to share the orbitals. They want to be alone, right? If given the choice. So that's why they want to be alone in this orbitals. Only if there is no other option, they want to pair. And it has been observed that half-filled and fully filled orbitals acquire extra stability due to symmetry. Please note, because of the symmetry, half-filled and full-filled have extra stability. Thank you. Visit examfear.com to watch free educational videos, try free online tests, get the best quality study materials, study from the best tutors and mentors, and much more. Thanks once again.